Okay, in today's lesson, we're going to extend our ideas from R2 to R3. As we've always said in the past, pretty much everything that exists in R2 does exist in R3 and it generally works the same way. So if we're looking at equations of vectors in R3, just like R2, we need to know a point and a direction, or we need to know 2 points. The only difference between R2 and R3 is we now have a z component. So when we're making our equations, we got to make sure we've taken care of that, whether it's vector form, or whether it's Cartesian form, or whether it's parametric form. Okay, the picture looks somewhat more complicated just because it's 3 dimensions, but it actually is the exact same picture we did when we did R2. We need to have an initial vector to get to our line, and then we need to have a direction vector along our line, and if we add those two things together, we'll end up with the vector that we actually want that goes along here by taking this plus a bunch of these like we did in R2. Okay, so our vector equation's got 3 parts to it. Sorry, 2 parts to it, but 3 components. It has the initial point, like we had before, plus it's got a direction vector. Just make sure you have an x, a y, and a z. Our parametric form has the exact same pieces, except for we have a third one now, z. Okay, so we'll start with a basic example. Okay, given a line through A and B, determine the vector and parametric equations, and then find 2 other points on the line. So we'll start off by figuring out, well, which way does AB travel? So we need to find our vector that joins A to B. So by doing our subtracting method, 4 minus 5 is -1, 5 minus 1 is 4, and 1 minus 3 is -2. I've got myself a direction. You might recall we can use any point that we want to. I'm just going to start with A because it's easy. And I can use any vector I want to as long as it's collinear with the direction vector we figured out. Now, it makes the most sense to actually use the vector, but you will come across equations that, call R2 here, where they've taken an answer and they've given a collinear vector, for example, this one, where they've changed all the signs. Okay, those mean exactly the same things. Parametric equations. So x would be 5 minus t, using the initial one. Okay, this one right here. Y equals 1 plus 4t, and z equals 3 minus 2t. Okay, so just exactly the same way we did in R2, but we're doing in R3. It also asks us to find other points on the graph or on the line. So pick values for t, whatever values you want. Start with a nice easy one. T is 2. 5 minus 2 is 3. 1 plus 4t when t is 2 would be 9. And if t is 2, 3 minus 4 makes -1. There's another point on the line. Call it point C. And if I want to find one more, let's just make D. If t is 3, 5 minus 3 is 2. 1 plus 12 makes 13. 3 minus 6 is -3. And there's another point on our line. The only difference in R3, besides vector, Cartesian, and parametric forms, is we add a third one, and we call it the symmetric equation. And the way the symmetric equation works is we actually solve all 3 parametric equations for the parameter t at the same time. So for example, if we had x equals the initial point plus t m in the x component, we could rearrange this and solve for t, and you'd end up with this, right? And that's all we've done here. And we could do the exact same thing as y and the exact same thing as z, and all 3 of those equations have to be equal to each other because they all share the same parameter. And this is kind of handy for figuring out our points on the lines, our points on the vectors. Okay, when we do solve this symmetric equation, we just don't usually show the t equals at the beginning. We know it's there, we know that's what it means, but we usually show this part right here. So if I want to take the previous example and use the symmetric equation, okay, so I'm going to take our parametric pieces here. So this, and we'll copy and paste it to the next page, just so we can take a look at the same time. Okay, I want to write this as symmetric form. So the way that's going to work is I'm going to take the x1 and solve for t. So I'm going to have x minus 5 equals negative t, or x minus 5 over negative 1. I'm going to do the same thing with y, so y minus 1 is 4t, so y minus 1 over 4, and z minus 3 equals negative 2t, so z minus 3 over negative 2 is t. If I put them all together, I get x minus 5 over negative 1 equals y minus 1 over 4 equals z minus 3 over negative 2. And there's your symmetric form. Now you might notice, and I'm hoping you do notice, that these things are your directions. If you actually look, m was negative 1, 4, negative 2. And these things are the values, your point. The only difference is it's always minus, the opposite sign. Right, our point was 5, 1, 3. If you notice, it's x minus 5, y minus 1, and z minus 3. So you can actually jump from parametric to symmetric very quickly and back and forth again. Yeah, so let's give this one a try. Symmetric form, really quickly, using the idea we just did. So x minus the value over the direction. Y minus the value over the direction. Well, that's weird. And z minus the direction. Now, sorry, minus the point, so plus 1 this time, over the direction. Now, we don't usually show y minus 6 over 0. That doesn't really make sense. Okay, so what we do in that case is we actually rewrite this. X minus 2 over negative 1, z plus 1 over 6. And we didn't write the other y part in there because you can't really divide by 0. So we just say y minus 6 equals 0. Or even better, I'll change that into y equals 6. Because no matter what, y is always 6 in this version. There's no way you can change it. So y isn't 6. And there's our quick jump to symmetric form for that one. Okay, that happens whenever we have a constant. Now, one thing to point out to you, okay, if we have two variables that are constants, it's not possible to write something in symmetric form. So for example, if you were to have a vector r, which was 2, 3, 4, plus, I don't know, 1, 0, 0, we wouldn't write that in symmetric form. Okay, because both the y and the z's are always constants. Okay, there would be no equals, there would be no cross multiplying, there would be nothing like that. Okay, so let's work backwards a little bit. Can put this back into vector and parametric forms. So back to vector form is probably the easiest way to do things first. So r equals our point. Okay, so 3. Be careful with the next one, right? We have 1 minus y, which is not the same as y minus 1. This is like saying a negative 1 minus a y, negative 1 plus y. And so our opposite sign is a 1 there. And here we have a 0. Our direction vector is 2, 3, and 4. Okay, so just be careful about order. Sometimes we write things in weird orders. The whole objective here is just like when you did quadratics, it's whatever makes the top equal 0. That's what your point is. Okay, so 3 minus 3 makes 0. 1 minus 1 makes 0. 0 minus 0 makes 0. Parametric form, x equals 3 plus 2t, y equals 1 plus 4t, and z equals 0. Oops, sorry, not 4t. Hang on, that's the right one. That's a 3t there. Y equals 1 plus 3t. Z equals 0 plus 4t, or in other words, just 4t. Here's your parametric forms. Okay, let's look at some different idea here. Determine the parametric equation for each of the axes. So in R3, we have our three axes. We have your x, your y, and your z. And each of those axes actually has equations. And if we want to figure out the equations, we can think about, well, if I go from 0, 0, 0 in the center, down along the x-axis, I'll get to a new point. Just for simplicity's sake, let's call that point 1, 0, 0. Remember this was 0, 0, 0. So if I want to figure out the parametric equation of that line, I could think of this as, first of all, think of it as a vector equation. What point is on that line? Well, the point 0, 0, 0 is on that line. And I have to go in the direction of 1, 0, 0. So parametrically, that equation is just x equals t, y equals 0, z equals 0. That's your x-axis. And the same is going to be true for every other axis, right? Like, you can all go from 0, 0, 0, and then along the y-axis would give you 0, 1, 0. So the only thing that's really changing is the direction that you go along each of the axes. So in this case, y would be t, and z would be 0, and this would be your y-axis. And then if you do the z-axis, well, x has to be 0, y has to be 0, and z would have to be t. Sorry, z would have to be t. This would be along the z-axis. Okay, because you go 0, 0, 1. And I picked the easy numbers, I used the ones, but if I had changed those things, I had chosen along the x-axis 46, 0, and 0, all that would be is a scalar multiple in the direction of the x-axis, right? It's the same value, just a bigger multiple. Okay, now problem solving for us. So show using the symmetric and parametric forms that the point 1, 2, 6 does not lie on this line. So this is our symmetric version right here, obviously. Our parametric version would be x equals 4 plus 3t, y equals negative 2 plus t, and z equals 6 plus 2t. And I'm going to show it with both. Now down the road, I won't make you do both. I'll say pick one or the other, and just depending on which format you have, there's different ways you can show this. So how can I show that 1, 2, 6 does not lie on this line? Let's do this one first. So 1, 2, 6, if I put that in for my x, y, and z, I'll get 1 minus 4 over 3 should equal 2 plus 2 over 1, and that should equal 6 minus 6 over 2. Now the emphasis there is should. So let's see what happens. On the top I get negative 3 over 3, I get 4 over 1, and I get 0 over 2. If I simplify that, I get this. Well, that's obviously not true. All three of those are not equal to each other, much less two of them. So this is not on the line. They would all have to be equal for that point to exist on that line. So if we use this, that's the symmetric version. If we use the parametric version to do the same thing, I'm basically solving for the parameter, right? I'm saying, okay, what happens to t, which is kind of what we did when we did symmetric. So 4 plus 3t, I put the x in. 1 minus 4 is 3t, negative 3 is 3t, negative 1 is t. If I try the y one, we get 2 equals negative 2 plus t, negative 2 plus t. If I solve that, I get 2 plus 2 is t. So I get 4 equals t. And obviously 4 equals t and negative 1 equals are different. We don't have to worry about the z1, not on the line. Now, I hope you recognize and realize that this is doing exactly the same thing. It's just already rearranged for us, right? If you look at the math, 1 minus 4 divided by 3 is what we did in these two steps right here. So that's why the symmetric version can be really handy, because it tells you a point on lines really quickly. And a lot less work to do that. Okay, last one, I think. Show that V and U are parallel but not coincident. So this goes back to yesterday's lesson. And we said things are parallel if they have the same directions or normal vectors. And coincident means that they were the same line, and we're trying to show that they are not the same line, not coincident. So what does it mean to be parallel? Well, it means they have to have the same directions. So for V, our direction vector is negative 1, 1, 2. For u, our other direction vector, so m2 let's call it, m1, we get 2, -2, and -4. And what do we notice? We notice that m2 is -2 times m1. Okay, so it has to be parallel. Coincide means that they're the exact same line, which means every point from one line has to be a point on the other line. So let's test it out. Let's see if the point 1, 6, 1 lies on U. And if it does, that means they're coincident. If it doesn't, they're not. So how do I test that out? Well, the easy way is to use my either parametric or symmetric equation. We said symmetric is actually faster than parametric, even though they do the same thing. So let's make this symmetric. So x minus the x value would be x plus 3 over the direction. Y minus the y value over the y direction. And z minus the z value over the direction. Let's take our point and plug it in the right spots. So 1 plus 3 over 2 should equal 6 minus 10 over -2 should equal 1 minus 12 over -4. We'll get 4 over 2, -4 over -2, and -11 over -4. And I'm hoping you guys can see what's going on here. 2 is 2, which does not equal 11 over 4. So that point is not on the line, which tells us these are parallel but not coincident, because that point did not lie on that line. And that's the end of equations in R3.